and refresher course on astronomy and astrophysics. So today, so my name is Debarati Chatterjee. I'm associate professor and chairperson of LIGO India Outreach. I'm working at the Inter-University Center for Astronomy and Astrophysics in Pune. So today I will be talking about compact stars. So let me share my slides. All right. So we will be taking questions in the end, or as you already know the rules of the game, so you can also send me the questions via the form that you have already seen in other talks. So right, so today I will be talking about compact stars. So this is a two-lecture series. So today I will be introducing the concept of compact stars, and tomorrow I will be telling you a lot more about how we understand about the interior composition of these kind of objects. So as you already have been you have already attended lectures of during the course of the summer school, and you have already heard several times about compact stars. So it's pretty much like a spoiler of a movie. You've already heard about how they are formed, and you have already had a little bit of a background of the extreme complex physics of compact stars. So today and tomorrow, I will be telling you a little bit more about why these objects are so fascinating. So let's get started. So what are compact stars to begin with? So when we talk about compact stars, so these are objects, or these are compact objects which are formed at the end point of evolution of massive stars. So in this figure, so you must have seen, you must have heard lectures from Professor Dipankar Bhattacharya, who talked about stellar evolution, and you have heard about the evolution of massive stars. So here we are talking about the compact remnants of the evolution of massive stars. And by compact stars, we mean white dwarfs, neutron stars, and black holes. So black holes are called compact objects. So in the stellar evolution lectures, you've already learned that white dwarfs, neutron stars, and black holes are formed from different types of stars. So these stars can be differentiated by their zero-age main sequence masses. So stars which are light, so something like the sun, they are which have masses between 0.04 to about 8 times that of the sun. They end their lives as white dwarfs. On the other hand, massive stars, which have initial masses going beyond 8 solar mass up to 25 solar masses, these can form neutron stars at the end of their lives. Whereas stars which are even more massive to begin with, so more than 25 solar masses, they end as black holes. So although nowadays, with a lot of multi-messenger astronomical data, nowadays we are even digging further into the origin of these kind of objects. So this is a topic of active research. So just to give you an idea about why we call them compact and why do we study them at all. So you have a comparison here between Earth and Sun. The sun is the most common or the nearest star to us. So we would like to compare white dwarfs and neutron stars to the properties of the sun. And as you can see here, there is a table of mass, radius, compactness, surface gravity, and mean density. So you can see here comparatively, compared to the sun, the white dwarfs typically have masses of around half of that of the sun, or one solar mass. Neutron stars can have masses between 1 to 2 solar mass. This is observationally established. Radii, on the other hand, white dwarfs can have radii which are as large as 5,000 to 10,000 kilometers, whereas neutron stars have radii of only about 10 kilometers, so like the size of a city. So you can compare, or you can calculate the compactness of these objects by taking a ratio of the mass to the radius. So you can see how compact these objects are. And so the larger the compactness, the more compact it is. And also you can see from the large surface gravities that these objects are highly relativistic. So general relativity becomes an important property for these objects. And also, like you can do a back of the envelope calculation for the mean density as well. You have the mass and the radius. So mass divided by volume gives you mean density. And so for white dwarfs and for neutron stars, you can see that the densities are enormous. For neutron stars, you can see these densities are actually going up to 2 to 10 times that of nuclear saturation density. So the dense nuclei that you can prepare in terrestrial laboratories, neutron stars exceed those by 2 to 10 times. So this gives you an idea why we are studying these objects. So these objects are basically like astrophysical laboratories, like cosmic laboratories, to probe extreme properties of matter, which we cannot encounter here, even with the best of technologies, even with the most extreme kinds of terrestrial experiments. So how are these objects formed? So for a normal star like the sun, so at the bottom you can see this is the life cycle of the sun. So any a normal star, so they so they generate thermal energy by nuclear fusion of light elements, and the stellar structure is determined by the balance of the thermal pressure, which is produced by nuclear burning, and gravity. So you have already heard about this from Dipankar's lectures. And so this thermal pressure support is what keeps the star burning, and which is why we have hydrostatic equilibrium in the star. Now, when the hydrogen fuel in the core of these stars is exhausted, there is no more thermal pressure left to support the star against gravitational collapse. So now the star starts to contract, the core starts to contract under gravity, raising the temperature and starting helium burning. So this is the next heavy element in the periodic table. So you can see that now helium will start to burn to produce carbon. Now, what happens is in low mass stars, so like the sun, or between 0.04 to 8 times that of the sun, this nuclear burning does not proceed beyond this is not the whole story. This can be even more interesting in the case that massive stars, which are more massive than 8 times solar mass, they can continue this nuclear burning. The reason is that these massive stars can have enough temperature and pressure to cause the carbon to fuse further. So, in the same way, nuclear burning continues to fuse carbon to oxygen, then neon, magnesium, silicon, iron, etc. So, heavier and heavier elements are produced, forming an onion like structure, internal structure. Now, you must have already heard this from the Bunker's lectures. So, iron, now this we know from nuclear physics, that iron is the iron family, the group of elements is the most stable for a stable nucleus. So, fusion of iron does not produce energy. So, now that if iron, and the reason is you can see here from this figure, burning will stop, which means that the thermal pressure support, which was supporting the star against gravitational collapse, is now gone. So it means that the core will start to collapse. So this is what results in what we call a supernova or a core collapse supernova explosion. There are also other types of supernova. So as these outer layers start to collapse towards the center, Am I back?
Yes.
Okay, I will share my screen again. I lost connection for a second there. Until where could you see the slide? Can somebody please tell me?
Can you go back one slide?
Sure, I will do that. Okay.
I think you are here. This
Okay.
slide.
Thanks a lot. Great. All right. So we were talking about the supernova explosion. So when the thermal pressure support is gone, the core starts to collapse towards the center, and this shrinking core heats up, which causes photo disintegration of these iron nuclei to helium nuclei and neutrons. Even these helium nuclei are split into protons and neutrons through photo disintegration. Now, while the core density increases, it becomes energetically favorable now for the electrons and protons to combine through a process called electron capture. And this process produces neutrons and neutrinos. So the neutrinos, as we know from the properties of neutrinos, these don't interact with normal matter. So they freely escape from the core and take away energy, which means that the collapse now starts to accelerate even further. So the collapse can only be halted by something called degeneracy pressure. So this I will come to later. And otherwise, the collapse halts only when nuclear densities are reached at the center. The infalling matter rebounds, producing a shock wave that expels the outer layers into the interstellar medium. So this is something we called the core collapse supernova explosion. So there are also other types of supernovae, and here we are talking about the core collapse type, or also called supernova type 2 supernova type 2 explosion. So right, so here you can see these beautiful pictures. If you go to the to websites like the NASA website, so you can see beautiful pictures, images of supernova explosions and remnants that are left behind as a result of this fascinating astrophysical process. And so now, if we look at the remnant that is left behind, so if the progenitor star is below 20-25 solar masses, then the degenerate remnant formed is a neutron star. So initially, the neutron star that is formed is hot, and it's called a proto-neutron star, and it still keeps cooling off by emitting these neutrinos until it forms a neutron star. If the progenitor star is even heavier, then it will collapse to a black hole. So just to look at an animation that explains this process, here you can see a main sequence star, which is burning nuclear fuel in its center. So thermal pressure support is there. And it goes through these different evolutionary phases until it ends in a supernova explosion. The outer layers are expelled, and you have this neutron star forming at the center. So this is the remnant which is formed. Now, we were talking about degeneracy pressure. So, is there any process that stops this collapse of of the outer layers during the supernova explosion? So you see that during the collapse, the nuclei, the protons, neutrons, all these come very close to each other because of the rapid where the interaction. So can you hear me now? Okay, thanks. I think the internet is very unstable today in Naika. Okay, so I will. So we were talking about the collapse of the supernova core collapse process, and so what happens is that when the electrons and protons come very close to each other, now the quantum mechanical effects start to become important. Now, both electrons and neutrons, if you have had already a course in particle physics, then you would know that electrons and neutrons are actually, they belong to a class of fundamental particles called fermions, which means, so this is because they have half integral spin as opposed to, say, photons, which have integral spin. So half integral spin means that electrons and neutrons can have a spin up and a spin down configuration. So it can accommodate two particles in the same state. And because of this property of having half integral spin, fermions obey something called the Pauli's exclusion principle, which means that they are forbidden from occupying the same energy state. When you try two fermions into the same energy state, they will repel each other. So this is something like you can imagine like bringing the same poles of two magnets close together. So so this kind of the Pauli exclusion principle actually results in a pressure because of degeneracy, because of the fact that they cannot be forced into the same energy state. So this is called the degeneracy pressure. And so when electrons and neutrons, when electrons come very close to each other, this effect becomes important. The electron degeneracy pressure is what supports white dwarfs against gravitational collapse. On the other hand, neutrons, for neutron stars, they are the ones which produce this neutron degeneracy pressure, which stops the star from gravitational collapse. Okay, so this is a quantum mechanical effect that can produce additional support against gravity. So just to give you a brief idea about what the internal structure looks like for compact stars so that you can at least have a mental picture. But I assure you that tomorrow we will be talking much more about the internal structure in detail. So today we will not dissect it too much further. Just to tell you that white dwarfs, typically, as you see on the left-hand figure, they have a thin hydrogen and helium shell, and they mainly have a carbon-oxygen core. So this is for carbon-oxygen type white dwarfs. There are also other type of white dwarfs with a different element in the core. For a neutron star, the picture is much more complex, and let's say with a lot of uncertainties even until now. And so it has an atmosphere, and the interior comprises of many layers such as the outer crust, the inner crust, the outer core, and the inner core. And in fact, the composition of the inner core is still unknown. So tomorrow we will be talking much more about the composition of white dwarfs and neutron stars. Today we will concentrate on astrophysical observations of Okay, we'll talk about astrophysical observations of both these compact objects with the help of multi-wavelength astronomy or multi-messenger astronomy. Let me give you an introduction to this angle of compact stars. So today we have, because of technological advances, we have a large number of both ground-based and space-based telescopes, and these are actually observing the sky. They are scanning the sky throughout the electromagnetic spectrum. So from gamma rays to X-rays, ultraviolet to infrared, microwave, and radio, we have today observations throughout these different multiple wavelengths. So for gamma, we have integral, Fermi, and there are upcoming missions like CT and Theseus. In radio frequencies, we have GMRT. There are also talks of the upgraded GMRT, SKA, and so on. We already have a multi-wavelength astronomical facility called AstroSat. You must have heard about AstroSat during these lectures. So other than that, in X-rays, we have the NICER mission. I will talk particularly about this mission later in my talk, and also Athena and future missions which are planned, such as SVOM and LINX. And also in the optical band, we have an optical and infrared, we have LSST and the upcoming TMT. So all these currently observing facilities as well as future planned facilities give us a wealth of data about many astronomical objects, including compact stars. So just to give you an example, this is the Crab supernova remnant. So you can see the supernova remnant at different frequencies, but you see mostly the interstellar dust in most of them, except for X-rays. You can see the Crab pulsar. So at the bottom left figure, you can see the Crab pulsar, which is at the center of the supernova remnant. And this is visible only in X-rays. So you can see the advantage of multi-wavelength astronomy, that we can actually, like a puzzle, we can put together information from different wavelengths in order to construct a picture, a multi-wavelength picture of these astronomical objects. So from this observational data, we can derive a number of different quantities, global observables, which are extremely useful for us to determine what is the interior composition of the neutron star. So you can see here for neutron stars, spin period is one of the most accurately measured quantities. So neutron stars are said to be one of the most accurate clocks in the universe because pulsars have very regular spin periods. If neutron stars or white dwarfs are in binary with another companion star, or if there is so in that case, from Keplerian features of the orbits, we can determine their masses. Moment of inertia can also be determined for neutron stars from their precession, for example. If you can measure the spectral lines for these compact objects, then from these spectral lines, you can determine what is called the gravitational redshift, and gravitational redshift depends on the mass and radius. So if you have the measurement of the mass, then you can determine the radius and so on. Now, I will come to a discussion of all of these observables in the coming slides. So there are also other observables like radii, temperature, and magnetic field for that can give us a lot of information about these compact objects. So Professor Ajit Kimberly already gave you a very nice introduction about white dwarfs. So I will tell you a little bit more about white dwarfs again. So these very interesting compact objects. So a Sirius B was which is still the closest and brightest white dwarf. So this was observed back in, so I think first in the 1800s, and then its compactness was first determined back in 1925 from the gravitational redshift of spectral lines. So this is the reason actually why white dwarfs are called white dwarfs, because it was understood from its compactness that these are very compact objects, and it was called white because of its spectral from its spectrum. So so this was the first observation that came of white dwarfs, and then the theory came later. So the theory was actually constructed in 1926. So Dirac at that time put forward the Fermi-Dirac statistics, and Fowler was the first one to apply this to white dwarfs. So it was then understood, and this was explained, that electron degeneracy pressure was responsible for supporting white dwarfs against gravitational collapse. Now, in 1931, Chandrasekhar was the first one who worked out the maximum possible mass for a non-magnetized white dwarf. And this was shown to be about 1.44 solar masses. So I will also come to a detailed discussion about the Chandrasekhar mass in tomorrow's lecture. So for masses in excess of 1.44 solar mass, Chandrasekhar showed that electrons would become relativistic and the degeneracy pressure would be insufficient to balance the star's gravitational attraction, which means that it would collapse into a black hole. So this concept was put forward by Chandrasekhar, which at that time was deemed impossible, and it even faced severe criticism from his supervisor, Arthur Eddington. But as we know that this was actually a plausible and correct hypothesis, and for which Chandrasekhar was later awarded Nobel Prize in 1983. So on the right-hand side here, you see the relation between masses and radii of white dwarfs. So you can see that this maximum mass limit of 1.44 solar masses, the Chandrasekhar limit, can be evidently seen in this mass-radius relationship. Although I will come to other factors that can be important, for example, magnetic fields, thermal effects, and interactions can also change this value, particularly magnetic fields. So I will come to these details tomorrow. So how are white dwarf masses and radii determined? So masses, as I already said, so if white dwarf is in binary system with another companion star, so from the Keplerian properties of the orbits, one can determine its mass. Now, if the mass is known, the radius can be determined in the following ways. So we already, if there is a measurement of the luminosity, then from the Stefan Boltzmann law, we know that luminosity is related to the radius and also the flux of the white dwarf. So the flux again depends on the temperature. So if the luminosity and effective temperature can be measured, then its radius can be measured. However, there is a small catch here. The flux at Earth is not the same as the flux that is at the white dwarf, and they are related by radii. And I mean the radial distance from of the Earth and that of the distance to the white dwarf. So if imagine if r is the radius of the Earth and d is the distance to the white dwarf, then you can determine the flux of the white dwarf from this relationship. And the distance to the white dwarf can be measured by parallax. And there are also alternative ways in which the radius can be measured. Like I already said, if you know the mass and you can measure the gravitational redshift, so then the gravitational redshift depends on the compactness. So the ratio of the mass to the radius, and from there also one can determine the radius. So all this Professor Kimberby must have already outlined to you. Now we come to pulsars or rotating neutron stars. So pulsars were the first type of neutron stars to be observed. So a little bit of the history behind how these pulsars were discovered. So we already know that Chandrasekhar showed that massive stars will collapse, and Landau also in 1931, the same year, wrote an article about the maximum mass of neutron stars. Now, at the same time, Chadwick also discovered the neutron. So this happened in 1932. Although Majorana had predicted neutrons earlier, but this was never published. Soon afterwards, 1933, Bade and Zwicky introduced the concept of neutron stars using these neutrons that were discovered in 1932. In 1939, a few years later, Oppenheimer-Volkoff, along with Tolman, computed the masses of neutron stars using general relativity. So these are often called the Tolman-Oppenheimer-Volkoff equations. So we will also come to that when we compute the structure of neutron stars. And then we know about the historic discovery of Jocelyn Bell in 1967. So she was a young student at Cambridge and she was looking for quasars when she found these strange wiggles in the data that she scrutinized very carefully and came to the conclusion that they were coming from a very periodic source. And then at that time, it was not understood what these sources are. But soon afterwards, 1968, Pacini and Gould, they proposed the basic lighthouse model. So this image or animation on the right tells you what we think pulsars are. So they are basically rapidly rotating neutron stars. So this was established back in 1968, that pulsars are actually rapidly rotating neutron stars. Now, pulsars are basically rotation powered, but then there are also accretion powered pulsars in binary systems. So there are also these binaries emit X-rays. So X-ray binaries can also have accretion powered pulsars. And there is a lot of dynamics of neutron stars with its companion stars. If there can also be cases where these neutron stars the companion star actually goes through another cycle where it explodes in a supernova, and the companion also ends up in another neutron star. So in that case, it would be a binary neutron star system, and very rarely. So I think until now there was only one, if I know correctly, a double pulsar system. So these are very rare. So double neutron star binaries are not common, but the double pulsar binary is quite rare. So as you can see, neutron stars can have many different, can have evolution also in binary systems. So they can be both isolated or in binary. Now, to understand pulsars, we first have to understand this lighthouse model that was put forward to explain that. So this is also called the dipole model of pulsars. So this means that pulsars are powered by magnetic fields, and so basically the magnetic dipole radiation and the rotational power, they should be. So basically, if we want to calculate these, so you can see here the magnetic dipole radiation can be written in terms of the magnetic field, its inclination angle, and the period P. Now, if we want to equate it with the rotational kinetic energy, we know that the rotational energy depends on the moment of inertia and the period of the pulsar. And so if you take a derivative of the rotational energy, this gives you a relation with omega, the frequency, and omega dot. Now, if you equate the magnetic dipole radiation with the rotational energy, if you equate these two, then you get a relationship. And from this relationship, you can actually determine the magnetic field. So this is also called the dipole formula. And so this is what relates the magnetic field with the pulsar period, the derivative of the pulsar period, P dot, moment of inertia I, the radius R, and the inclination angle alpha. So on the right hand side, you can see a very popular depiction of neutron stars, and this is with the help of P and P dot, P versus P dot. So basically the spin period in seconds and the period derivative, which is dimensionless. It's second. So in this picture, actually, so you can determine a number of different quantities. So I will explain these to you. So first of all, this cluster at the center are what are the normal pulsars. So these normal pulsars are the ones which were like the one which was observed by Jocelyn Bell. And what else can be determined from this relation between the period and period derivative? So there are some other quantities that can be defined. One such quantity is called characteristic age of the pulsar. So this is a ratio of the pulsar period to the period derivative. So these lines that you see, these long dashed lines with different years marked here, 10 to the 12 years, 10 to the 9 years, etc. So these are the characteristic ages of the pulsars. Also the magnetic field, like we said, if you have P and P dot, and then you can determine B from the observations. So you can see these are marked by the other perpendicular lines marking the different magnetic fields. So 10 to the 10 Gauss, 10 to the 12, 10 to the 14, etc. So from this figure, you can see that the normal pulsars, like the one that Jocelyn Bell observed, so these have typically magnetic fields around 10 to the 12 Gauss. There is another important thing called breaking index, which can also be defined. So breaking index is can be defined by a ratio. If you actually take the, instead of the period derivative, instead of the period, you take the frequency, you differentiate it, and then if you take a ratio of the second derivative multiplied by the frequency divided by the derivative square, this is something which is called breaking index. And why is it important? Because breaking index actually tells you a lot about what is the source that is powering what is the power source of the kind of pulsar. So if it is a normal pulsar, like the one we are talking about, in that case, breaking index can be somewhere between 1 and 3. Whereas if it is depending on whether it's from gravitational waves or some other sources, then the breaking index will change. So actually measuring the breaking index can also give you an idea about whether it is the magnetic field which is powering the spin down or whether it is something else. Now, not in addition to this, afterwards, so after the discovery of pulsars, there were many other types of neutron stars that were actually discovered. So the pulsar that Jocelyn Bell found was in radio, so it was emitting radio waves. But then there were also discoveries of X-ray pulsars, gamma ray pulsars. So you saw that there are many astronomical facilities that scan the sky across the electromagnetic spectrum, which give us an idea about which actually led to the discovery of many other types of neutron stars, which we now call the neutron star zoo. And you can see on the left a list. I mean, this is not an exhaustive list. There are many other types of particles. And why are they given such names? The reason is that they don't fall into the same category as the normal pulsars. In some way or the other, they have a difference. And this is actually attributed to other things, like, for example, the evolution of the pulsar along with other companion stars, magnetic field decay, magnetic field spin-up, and many other dynamic events that change some of these properties which are given to normal neutron stars. So, yeah, so some of these objects are like magnetars, central compact objects, isolated neutron stars, rotating radio transients, fast radio bursts, and X-ray binaries, and so on. So just to give you, okay, maybe I will talk about some of these later during this talk. So many of these discoveries are actually listed in the Australian Telescope National Facility Pulsar Catalogue, also called the ETNF catalog. So this is actually a public catalog. So you can also go to this website and download data about pulsars and even calculate some of its properties. For example, if you have P and P dot, you can calculate the magnetic field and so on. Now, from these, like I was saying, from these observations, we can determine a number of different observable properties, global properties of neutron stars. And not only that, we can even observe that there are certain phenomena which require explanation, theoretical explanation. So this is what I will talk about in the next talk. So one phenomena that has been puzzling scientists since a long time is glitches in the rotational frequency of neutron stars. So for example, in well-known pulsars like Crab and Vela, which have very smooth, very regular spin down rates, which mean like, for example, you see at the bottom left figure, the omega, the spin frequency of the star measured as a function of time. This is very regular for the case of Crab and Vela, except for sudden changes. So there are like sudden jumps in the rotation frequency, and then there is a slow relaxation towards the regular frequency. So this unexplained phenomena is called a rotational glitch. And so there have been different explanations. Some people think that probably it is the crust cracking that causes this kind of event. Recently, the more successful model is that which suggests that neutron stars have a superfluid component in its interior, and rotation of neutron stars results in quantizing of vortices. So in laboratories, it has been seen that superfluids, if they are put in rotation, then they form kind of vortices, and these vortices are pinned to the surfaces, the top and bottom surfaces. So it is thought that the same phenomena can also happen in neutron stars. So these superfluids vortices can be pinned to the crust, and when there is a glitch happening, there is a change of angular momentum, there is a transfer of angular momentum between superfluid and normal components. So it is actually suggested that these observations of glitches are actually thought to be evidence for existence of superfluidity in the interior of neutron stars. What are the other things we can measure from these observations? So, like I said, masses. So, for white dwarfs, masses can be determined from Keplerian parameters, like the ones listed here. So, if you can measure orbital period, projected semi-major axis, eccentricity, longitude of periastron, and epoch of periastron passage, then you can determine the mass function. And from the mass function, you have the total mass, and if you can measure one of the component masses, then you have the masses of both of the compact stars in the binary system. So in the case of neutron stars, so in general, this can be done from timing studies of radio binary pulsars, and this has shown that neutron star masses usually lie within a narrow range of 1.25 to 1.44 solar masses, but there are exceptions. I will talk about these tomorrow. And in addition to that, neutron stars are relativistic. So, like I said, the surface gravity is very high. These are extremely compact objects and they have relativistic effects. So, these relativistic effects or post Keplerian parameters can also be measured in the case of neutron stars. So some of these are like relativistic advance of periastron. You must have heard of perihelion for the case of the sun. So this is something similar for the neutron star. Then gravitational redshift and time dilation, orbital decay, Shapiro time delay, and so on. So if a few of these Keplerian, post-Keplerian parameters are measured, then you can measure the masses of neutron stars. And this has been particularly very successful for the case of the double pulsar binary that I talked about. For that, the masses could be very accurately determined from measurement of several of these parameters. So this is a list of the neutron star masses. So you see most of them are clustered around a value of 4, which is a big neutron star mass. But there are also some larger masses which have been measured, and they tell us a lot about the interior composition of the neutron star. We'll talk about this tomorrow. However, you see that the most accurate ones are the double neutron star binaries, whereas X-ray binaries or white dwarf neutron star binaries have larger uncertainties. We talked about gravitational redshift. So gravitational redshift is actually the ratio. It is defined by the ratio of the emitted and observed frequencies, and is related to the compactness or m by r ratio. So if the mass is known, then the radius can be measured. So these from spectral lines, from X-ray observations, one can determine the redshift, which gives the compactness. Cooling of neutron stars are another very important quantity that can be derived from the observed flux and luminosity, and it also gives us a lot of information about the interior composition. Radius is one of the more tricky global observables to determine. Normally they are determined from thermal emissions from the surface. However, recently there has been a breakthrough by the recently launched NICER mission, or Neutron Star Interior Composition Explorer by NASA, which is using a completely different kind of technology, or they are modeling the gravitational, the general relativistic effects of pulse profiles of rotating hotspots. And this is actually resulting in a very accurate measurement of radius and claims to be able to determine radius up to 5% accuracy. So we already have some data from ISSAA, which is imposing important constraints on the neutron star composition. Moment of inertia is something else, so that can be determined from spin orbit coupling and for example, from precision in pulsars, we can also determine moment of inertia, and this depends on proportional to mass times radius squared. So again, if you can measure the mass, you can have an idea about the radius from the moment of inertia. Now, we were talking about the neutron star zoo. So, magnetars are one such candidate that I would like to point to. So, you saw this period derivative figure. So, normal pulsars lie in this band. So, there are some objects called soft gamma ray repeaters, which are seen in gamma rays, or anomalous X-ray pulsars that are seen in X-rays. So, they have very different values of period and period derivative, which indicates that they have surface magnetic fields as large as 10 to the 14, 10 to the 15 Gauss. Okay. And interestingly, there have now also been, so these objects of gamma ray repeaters and anomalous X-ray pulsars are also called magnetars together. And interestingly, they are now there are also discoveries of some intermediate objects somewhere between pulsars and magnetars, so also called high magnetic field neutron stars. And interestingly, all these objects show various astronomical features like bursts, like flares, and quasi-periodic oscillations, which also give us a lot of idea about their internal magnetic field configuration and a lot of other interesting physical properties because of their extremely high magnetic fields. So the last thing that I would like to come to are gravitational waves, and this is a very recent discovery. So this is actually the frontier of research we are talking about. And neutron stars and white dwarfs. So neutron stars definitely are one gravitational wave sources, both from isolated and from binary systems. So, for example, for neutron stars, any source, any kind of perturbation which is time varying and of quadrupolar nature, so it could be rotation, deformation, or oscillation that can result in gravitational wave emission. So we already talked about glitches and magnetar flares. So these could be sources of bursts of gravitational waves. If there are deformations on the surface, also called like a mountain, so it's not a mountain, actually it could be just a few centimeters in the case of compact objects like neutron stars, but any slight deformation on its surface because of rotation can also emit gravitational waves. The large deformation of neutron stars due to due to strong magnetic fields can also result in gravitational waves. So these are sources of continuous gravitational waves. Now, in addition to this, we also know that in terrestrial experiments, we have seen fluid oscillation modes. So radial pulsations, and also there are non-radial pulsations which have been observed in experiments. And this is something which is also known from astroseismology. So in case of solar oscillations or stellar oscillations, many such oscillation modes have been seen. In addition, neutron stars can have these fluid oscillation modes and also some space-time modes or W modes, which are typical for only strongly relativistic objects. So these modes are quasi-normal modes, and these are classified according to the restoring force that brings the system back to equilibrium. So there are fundamental F modes, there are pressure P modes, buoyancy resulting in gravity or G modes, rotation, something like the Coriolis force that restores rotational R modes, and so on. So the gravitational wave frequencies in this case are proportional to the rotation frequency of the star. So now that you have seen that neutron stars can actually emit so many different kinds of gravitational waves, now the question is, can we observe them? So the first indirect observation of gravitational waves came a long time back in 1974 when Joseph Taylor and Russell Hulse observed one pulsar, which is now named after them, Hulse-Taylor pulsar, and noted that this binary system was actually losing energy through gravitational waves, and they measured the shift of periastron due to this kind of merging of these neutron stars, and found that it was exactly following the general relativistic prediction of Einstein. So this won them it won them the Nobel Prize in 1991, and this was the first indirect detection of gravitational waves. Now, we know that neutron stars can undergo mergers, which means that there is an inspiral phase when they approach each other through emission of gravitational waves. There is a merger, which means that they fuse to form one object. And this resulting remnant object could be a neutron star, it could be a black hole. And then there is a ring down, which means that there are oscillations in this remnant object, which rings like a bell, and then finally gets damped in time. Now, what is interesting is that if we so simulations also showed us that these neutron stars, when they are in a binary merger, they can tidally deform each other because of their strong gravity, and this tidal deformation actually shows dependence on the underlying composition of the neutron star. So we'll talk about this further tomorrow. So because of this, so this was motivating for to detect directly gravitational waves, and therefore over the last 10 years there have been many facilities built around the world. So LIGO in the US, so you see the Hanford and Livingston sites, and Virgo in Europe were built in order to detect directly gravitational waves. And finally, gravitational waves were detected from a neutron star merger in 2017. And not only in gravitational waves, there were simultaneous detections in all the other different electromagnetic frequencies. And this actually opened up a new window to multi-messenger astronomy. So currently, there are, in addition to LIGO and Virgo, there is also the GEO in Germany and Kagra facility in Japan that are operating. And you probably already have heard about the LIGO India project from Sanjit Mitra's lecture. And so this is supposed to even increase the source properties. So it's a localization and its detectability much more manifold by construction of LIGO in India. And there are also many other facilities like the Einstein Telescope and Cosmic Explorer, the LISA mission. LISA will be more relevant for black holes. So all these future missions will also look further into the gravitational wave universe and give us much more information about neutron stars and white dwarfs. So I will stop here for today. And thank you for your attention. You can ask me questions, and we'll continue tomorrow to look into the interior of these objects. Thanks. I think there are some raised hands and some questions in the chat. So I will first go to the questions. Second. All right. I don't know who was first. Deepakar, do you want to ask your question?
Ma'am, my question is, am I audible, ma'am?
Yes, you are audible.
Yeah, my question is, what is the source of magnetic field that is produced inside the neutron star? Because the magnetic dipole moment is shown, but what is the cause of that magnetic field? Why those neutron stars are having magnetic field? They are having only neutron field.
Right. So I will explain this to you. So, so neutrons, like I told you, neutron stars are formed by collapse of massive stars. So normally when there is a collapse of a star, what happens is there is conservation of magnetic flux. which means that so this depends, the magnetic flux actually depends on the magnetic field strength divided by its area. So what happens is when it is shrinking to form a compact star, the magnetic field blows up as a square of its radius. So what happens is the magnetic field blows up many times and forms these 10 to the 8 to 10 to the 12 Gauss magnetic fields you see in a pulsar. But then there are also other models which suggest that there is a dynamo mechanism which results in amplification of magnetic field, a seed magnetic field. Otherwise, we will not be able to explain magnetars or extremely high magnetic field pulsars. So I hope that answers your question.
Thank you, ma'am.
Sure. Shlok sir, please ask your question.
Hello, ma'am. Am I audible?
Yeah, you are.
Ma'am, I wanted to ask, is the rotation frequency of the neutron stars different from the frequency with which its internal fluid vibrates?
Internal fluid vibrates. Yeah, so it's I mean, you are talking about gravitational wave emission.
Yeah, in the end, you talked about the vibration oscillation of internal fluid, right?
Right.
Like
Yeah.
it
So
oscillates. So
yeah. So actually, these all these different modes are actually produced by different kinds of mechanism. Like for example, discontinuity in density, or it could be rotation. So rotation in the sense like Coriolis forces and so on. And in these cases, although the gravitational wave frequency is proportional to the rotation frequency, but they are not exactly multiples. I mean, they are not exactly the same. And the reason is that these modes of oscillation are not, I mean, these are perturbations which are generated inside the star. So they are not exactly the same as the rotational frequency of the star, but they are dependent on it.
okay, thank you, ma'am.
Sure. Chetan, please ask your question.
Ma'am, my question was that
Can you
you
speak
said that
louder?
yes, ma'am. So, am I audible now, ma'am?
Yeah, you are audible.
Yes, ma'am. So, I was asking that you said about the moment of inertia of neutron stars, no?
Sorry, the moment of
Moment of
yeah.
inertia of neutron stars or pulsars. So, ma'am, how we measure the how can we measure the movement? That you said that if we get the mass of that pulsar, so we can get the idea of radius. Huh? So how do we measure the moment of inertia?
How do we get the radius from the moment of inertia? So I mean, like for example, you can see this sphere here. So this moment of inertia is dependent on the mass and the radius squared. So this is for a general solid sphere, but in general the moment of inertia is also I mean, it is proportional to mass times radius squared, but also there is an exact expression that I have not given here, but we can
Yes,
talk about this tomorrow. So yeah, there are some more details in the expression, so I did not put the expression today. But once you know the moment of inertia and the mass, then you can read out the radius.
so ma'am, I was asking that why, matlab, how can we matlab, how do we get the idea of moment of inertia? Ma'am? Means exact
How do we
value of
determine it?
yes, ma'am, moment of inertia.
Okay, so yeah, I mean, I have not put everything on my slide, but in general, um, so this can be determined from the spin orbit coupling of neutron stars. You can see here a kind of a rough cartoon, or else from the precision of the star also. If the star is precessing around the center. So for all this, I think I would refer to you like textbooks like, for example, Shapiro-Tukolsky, or I think probably also in Weber's book. So all these books talk about moment of inertia of pulsars. So
So
you can have a look how they are determined. Yeah.
thank you, ma'am.
Shubhadeep,
Hello, ma'am.
hi.
So, ma'am, you have discussed about how the new stars are born and die via supernova explosion and all that. I
Mhm.
wanted to know how the primordial stars or first stars are born. Does they same way generate the required gravitational potential well? And also, addition to that question, I have read very recently somewhere in some distinct quantum spectrum we have found elements. Now, elements synthesizes to stars. So, as we know, quasars are early galaxy making stage. So, how can there will be a star without having a galaxy? Can you please explain this, ma'am?
Uh, are you talking about evolution of the primordial stars? So this is not what I have covered in my lecture. This probably Professor Dipankar Bhattacharya must have covered. So the stellar evolution and how these the progenitor stars were formed. Um, if you have not followed his lectures, then you can try to find his lectures on the YouTube channel of IUCAA. Yeah, he also explained how these stars evolved um, through the different phases, if that is what you're asking.
Okay, ma'am, thank you.
Okay. There are some questions in chat. I will try to go quickly through them. Why do these stars increase in size by turning into red giants before they contract? Yeah, the same thing. So please look at, so this is a complicated process, and I'm sure Professor Dipankar explained this with the help of Hertzsprung-Russell diagrams, how these go from one phase to the other, go into red giants and then contract and so on. So please go through his lectures on stellar structure. Can you explain in detail about gravitational redshift of spectral lines? Um, Gravitational redshift is basically uh, the emitted frequency is not same as the observed frequency because of relativistic effects, because these compact objects have general relativistic effects, basically because of strong gravity. So this difference in the two frequencies is defined by the redshift, and it can be shown by from the stars, what can I say, metric. You can, I think you've taken general relativity lectures, right? So from the metric you can show that this is actually related to the compactness, the ratio of the mass to the radius of the star. I'm sure this probably, if you've not taken the lectures, so please look at last 2020's lectures of Professor Shukanta Bose. He must have explained this. What is the difference between a supernovae formed by carbon detonation and that formed due to iron fusion? What determines which of these processes happen? So, carbon detonation. So that is, you mean between supernova type 1 and type 2? Gayatri, if you're here. So the difference between the types of supernova. So the type 1 supernova, for example, is formed in a binary system of a white dwarf with a companion star, whereas um, the iron fusion, so the core collapse supernova, this happens in at the endpoint of massive star evolution that ends in. I have already told you that these type of stars are formed from progenitor stars having masses between 8 to 25 solar masses. So this initial mass and interaction with the binary, this is what determines what kind of supernova is going to happen. Okay, there's a question. In your first slide, you mentioned set of mass ranges for white dwarf, neutron star, black hole, but Chandrasekhar limit gives a different mass version for white dwarf and neutron star interface. Um, Okay, this is an interesting question. Maybe I will take this up in detail in tomorrow's lecture, so I can show. I'm going to talk about the equation of state and the determination of the Chandrasekhar mass limit analytically. So I will talk about this a little bit more tomorrow. In Hull's-Taylor prediction, does gravitational wave amplitude still arise before the ringing occurs? This is not the, wait. So Hull's Taylor prediction was about the how the orbit changes, so the shift of periastron as a function of time, and they found it to be exactly according to general relativistic prediction. So this is not what. Uh, so the figure I was showing on the right, so this in spiral merger ring down, this is for any merger, but they did not talk about the gravitational wave amplitude because Hulse and Taylor did not directly observe neutron stars. They observed it indirectly from the orbital motion of two pulsars from the electromagnetic observation. Whereas the gravitational wave amplitude I'm talking about, this is for from gravitational wave observations. Okay. Other hotspots on neutron stars similar to sunspots in their origin. Yeah, you can see that. So, although it's not exactly the same, but I would say both are caused by magnetic field. So, in the case of neutron stars, you have a dipole field. In the case of the sun, you have a different kind of magnetic field configuration. But still, you can say that. Yeah. What are the observables for P mode, vibration, etc.? Observations are the damping time scale and the amplitude, the frequency and amplitude, the frequency and damping time scale are observed for these modes of oscillation. Uh, Entropy always increases, so how is the collapse of a so how the collapse of a star balances this definition means, and if a celestial object is perfectly symmetrical, how do we detect them? I didn't understand. It's a very long question. Uh, okay, I will try to address this. If I have not answered any of your questions, please send it to the question sheet. I will just check if the question sheet has been addressed. Okay, there is one question. You have mentioned above pulsar spin is accurate, but we have seen timing analysis over a period of time. Okay, I can't read the full question. Yeah. But we have seen by timing analysis over a period of time, the spin period also changed something greater than 5 sigma. So if spin period changes with time, then it's not accurate anymore. Okay, so yeah, so in general, the spins are so I think I can explain from the magnetic field picture. Um, right. Um, so the spin, yeah. So like I said, the spin of the star is something that, or even from here you can see, right? So the spin periods of the star. So these scales are so this is in log scale. Okay, so the spins are actually very accurate, but the spin derivative can also be measured from the very accurate timing analysis of pulsars, and you can see how small they are. So they are of the order of 10 to the minus 12, 10 to the minus 14, and this is these are very small changes, and this change happens because of magnetic spin down. So it means that the system is actually losing energy through magnetic dipole radiation, and this is what gives causes this very small change in the spin periods. Okay. There is a hand up. Okay, I think this will be the last question. We are already way beyond time. Yeah, can you please, yeah, ask your question?
Am I audible? Good morning, ma'am.
Yeah, yeah.
My question is related to that question which I put up in the chat. That observables for P mode, co-rotation, etc. You had that slide on neutron star astroseismology.
Okay, yeah.
So I was just wondering if are there any observed any what do you say any graph or anything which just where you can demonstrate how these different modes uh, how they come out in those graphs like
Yeah,
some
unfortunately, I don't have a slide for that. Maybe I can add one tomorrow to
yeah,
show,
yes,
yeah, how they are, they can be distinguished from,
distinguished, yeah,
yeah,
exactly, yeah,
okay.
okay.
Okay, thank you very much for attending my lecture. So, hope to see you all tomorrow. If you have more questions, add it to the chat. I'll try to address it before my lecture tomorrow. All right, bye.
Okay, fine.